LINBIT's mission is to protect your data. And how are we doing that? So we are protecting the data by replication. And at the core of our data plane, we have a software component that's called DRBD. And when this orange box is the Linux kernel, its DRBD gets inserted at a certain place in the IO stack. And from there, it can mirror everything to one or multiple secondary nodes and replicate your data. And reads are usually carried out locally. And we are zooming out of the picture. And now the whole left side is the primary role. And the DRBD device is in primary role in the moment it's opened. So in the context of CloudStack, the opener would be KVM. So in the moment KVM opens the virtual DRBD device, it's primary. Migrating a VM somewhere else is pretty simple. Just the manager needs to stop the KVM process, then it demotes the secondary and start it somewhere else. It can also replicate multiple volumes in a consistent way. So that is replicating often volumes of different physical properties, like let's say one very fast volume and a very slow volume, and it can replicate them in a consistent way, obeying all the right of the right dependencies. It is also not a two-node thing, so it can mirror to multiple secondaries in parallel. Up to 32, but nobody needs 32 copies of his block data. And by the way, each replication link might be synchronous or asynchronous, and you can switch that at runtime. It also has what we call a diskless mode of operation. That means you have a node and the DRBD device is primary here. So it is accessed, let's say, by the KVM process. But only replicas on different nodes. So if there is a read coming down, a read request from the virtual machine, DRBD can decide where to send the read request, and it will load balance between those nodes. If it receives a write from the KVM process, it sends it to both nodes concurrently. That was it already about the data replication part. Now, keeping services online, that's important as well. So we support failover clustering, and this component, this DRBD reactor promoter, that is also embedded in the HCI appliance we will see later. And it is used there to keep the CloudStack manager running all the time, even if we lose nodes. Apart from that, we also have deep integration with container orchestrators like Kubernetes and with virtualization and cloud platforms like Apache CloudStack. Now, another important aspect is our control plane, and that's called LINSTOR. And LINSTOR comes with two components. One is the LINSTOR controller. So you will have one LINSTOR controller in your cluster running, which can have standby locations. So it is highly available. And on each node in your cluster, you will have a LINSTOR satellite. So satellite is the node agent. The satellite is completely stateless and configurationless. So all you need to do is you need to have the daemon running. The control, on the other hand, that has an embedded database, it's stateful. And so it's the controller that reaches out to the satellites, and it uses the satellites to do things on the machines, like creating logic volumes, configuring DRBD, taking snapshots, resizing volumes, etc. On top of that, we have the RESTful API, and through the RESTful API, you can use a CLI, a graphical user interface, or you do all your relevant volume management through a connector which is embedded in Apache CloudStack. So it's completely transparent to your CloudStack. Now let me give you an example how all this could work. So here in this example, I have a system of 6 hypervisor nodes. So all of them have the CloudStack agent installed. They have built-in storage devices in each of those nodes. And we have the LINSTOR components and DRBD components installed everywhere. Now, if LINSTOR gets a request to create an image in the primary storage, so primary storage as in CloudStack primary storage, we have a certain, let's call it storage class associated with that. Let's assume the storage class wants to have 2 replicas, and CloudStack wants to create this orange VM. Then we get the request, and we know on which node the VM will initially run. So LINSTOR creates a replica here and a second replica somewhere else. The same happens with the black VM. And you may notice that we always have one replica co-located with the actual VM. And that has the advantage that we can execute read requests very fast because we do not need to add network latency. We can fulfill them purely locally. Now in such a cluster, we can of course live migrate a VM. So move a VM somewhere else, maybe at a hypervisor where we don't have a local copy of the replica of the VM image. That is of course possible. Now it is from point of view of DRBD completely diskless and has to execute all the reads over the network. LINSTOR allows you to configure an automatic policy that it moves the storage to a running VM if it runs for a certain time without having a local replica at its current host. But that's completely optional. So you could set that, let's say, to 60 minutes. And after the time, LINSTOR would check, oh, is here enough storage space available in the volume group? And if yes, it creates a new logic volume, adds it to the DRBD config, DRBD does the resync, and after the resync finished, it will remove this replica because the storage class only wants 2 replicas. So I hope that gave you an overview how LINSTOR and DRBD works and provides highly available virtual volumes to your virtualization workload. Where is this used? It's used a lot for transactional workloads, like running databases or message queuing systems in your virtual machines or containers. Adding a few words about LINBIT and that all this software we are talking here about is open source. So our business model is purely to selling you support subscriptions to the open source software. We are a company of about 40 people. 25 of us are located in Europe, about 15 in the United States. And we have an exclusive partner in Japan. Here are some of our bigger named customers, and let's move on. And last but not least, we have pretty good performance. I would say maybe the best in the industry. So where is that coming from? It is coming from our data path is completely in kernel, avoiding context switches, allowing certain kind of optimizations. We allocate our backing volumes in the moment you create the virtual volumes. And again, that saves time when we do the actual I/O. We are building on existing components, not only because we're lazy, but because to keep your day 2 operations easier, because your operating people might already be familiar with some of the components. And last not least, it is very well suited to be used in a hyperconverged way because it's very lightweight in the amount of memory, DRAM, it consumes, and in the CPU cycles it consumes. So here I have some IOPS numbers which are of course great. So from 2019, I know that's a little bit dated, but also from 23, which is pretty amazing that only on 3 servers we were able to achieve 25 million IOPS. So you find these complete paper sets in our blog if you search for it. Okay, and I think with that, I step out of the way and pass the word back to Michael.